AP Stats, kids. It's Wednesday, April 22nd. Thanks for coming back. Hope we have a good day. Today's day 3 of probability. I did probability on Monday. I don't want to say basic probability, but you know, so some more general terms. We did conditional probability from a two-way table, those types of things. Mutually exclusive versus independence, I think we talked about. Luke did binomial and geometric yesterday, which is always kind of fun. I actually sort of like those too. And today I'm going to do what we call random variables. So we're going to wind up with probability today. Again, 3 full days of probability, which hopefully helps. It was a topic that students in a survey, all the consultants had a training last year, and it was a topic that students struggled with. So Luke and I really wanted to do a good job with that. I think tomorrow Luke has sampling distributions and central limit theorem, super important for statistical inference, really sets the stage. Friday is, I think, free response FRQ Friday. Luke's going to do Thursday and Friday. And then next week, we're going to shift towards sort of reviewing for the exam and how to use your calculator efficiently and formula sheet and all that good stuff. So let's dive right in for today. We'll look at the homework. Again, my name is Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. Cold up here today. We had a dustin', as we would say. It's kind of a New England saying, I think. A dustin' of snow means when you wake up, there's just a really thin film of white on your cars and grass, and it's already since melted. But it's kind of cold up here. It still feels winterish, unfortunately. Luke, he teaches at East Kentwood High School in Michigan, and he and I were talking today. So he and I are good friends. So this was the homework from last night. This was the problem that Luke left with you. So a popular computer card game keeps track of the number of games played and the number of games won on that computer. Okay, again, I just call this setting the stage. It feels like you either win the card game or you don't win it. You win or lose. The cards are shuffled before each game, so the outcome of the game is independent from one game to the next and is based upon the skill of the player. Okay, that makes sense. I like that independent word. Let X represent the number of games that have been won out of 100. So we're playing just 100 games, or a total of 100. That's a finite number. So I'm leaning towards binomial here, but let's keep reading. Under which of the following situations would X be a binomial random variable? Okay, so we're in a binomial setting here. Again, here's the same problem. So before I actually started to work on the problem, I just made some real quick notes down here to myself. When I think of a binomial setting or binomial probability, I think of four things that I need. And I know Luke talked about this yesterday. We have 2 outcomes, a success and a failure, win, loss, you know, in, out type of deal. We have independent trials. Well, we did see that word up here somewhere, so that was good. So it feels like we've met that condition. The number of trials is finite, meaning fixed, or we can count them, it stops. Determined in advance. Well, I think we had that, right? Didn't it say we were going to play 100 games? So that feels good. It feels like I've met those 2. I guess I have met the first one as well, right? We either win or lose the game. It didn't actually say lose, but it feels like we win or lose. And so I kind of focused in on this 4th one here, the same probability of success for each trial. So that's sort of what I was looking at before I did the problem. So A, all games were played by the same player whose skill improved over the course of the 100 games. Well, if your skill is improving, that feels like your probability of success is changing. So I don't think it was that one. A group of 5 players of different skill levels. I think I honestly stopped right there and said, well, different skill levels, that means different probability. It's not going to be that. A group of players of different skill levels, that again, that was sort of my little clue there. So I think I crossed that one out. 2 players of equal skill each played 1 game a day for 50 days, and their skill level did not change from day to day. So I sort of like that one, but to be honest with you, I said, well, 2 and 50, is that going to be the same as one person playing 100? So I wanted to keep reading. D felt pretty good to me, but I did want to just sort of keep reading and see what E told me. So 2 players of different skill levels competed, and so I actually did cross that one out. And so the answer is D here. And I actually really like this. You know, Luke and I sometimes talk about the problems we're going to pick, and sometimes we don't. And we just surprise each other with what the homework is for the next day, and he and I have to sit down and do it. I really like that. You know, I can't remember a problem in my textbook where, you know, we said 100 games where we had 2 people. So that felt really cool to me, and it was a little different, and so I really like that, and hopefully you guys really like it as well too. I had to think about it, and you know, it was a good little problem. So anyway, that was from Luke's session yesterday. So again, there's just some websites. I think this has been a typical slide of mine. Anything, all updates on your exam are here. You can find the schedule for what we're doing. There's more information coming, so stay tuned. And I do think at some point we're going to have like a practice as to how you can upload, you know, some more details as to how you can upload your answers. So stay tuned for that. College Board's working probably 24/7 to try and get this ready in a short period of time. More good stuff coming. Stay tuned. How's that? So today we're going to talk about random variables. And so the value of a random variable, the values of a random variable are the numerical outcomes of random behavior. Okay, makes sense. A discrete random variables. So discrete just means that there's a finite number of outcomes. I can count them, et cetera, as opposed to infinite. So we do a lot of discrete random variables in this class. So a discrete random variable is a variable that can only take a countable number of values. We know how many there are. Each value has a probability associated with that, so I can calculate the probability of that. And we talked about this, I think, on Monday when we talked about the sample space. The sum of the probabilities over all of the possible values must be 1. Super important, and I'm going to use that when I actually start to do some problems later this afternoon. I want to make sure that all of my outcomes add up to 1, and that sometimes helps me solve the problem. So, you know, I like to think of a random variable in its super simplest terms is a random event where I perhaps know what the outcomes could be, but I just don't know what's coming next, and that's the random behavior. So if I flip a coin, I realize I'm going to get heads or tails. I just don't know what the next outcome is going to be. If I roll a 6-sided number cube, a dice or a die, I know I could get a 1, 2, 3, 4, 5, or 6. I just don't know what's coming next. I can quantify each one of those outcomes and put an associated probability. And so I would define those as random variables. We're going to talk about adding means and standard deviations and whatnot. And so for 2 independent variables, x and y, we can add the variances. We cannot add the standard deviations. That's a little tricky. My students will sometimes struggle with that, and I think I have 2 multiple choice that try and get right to that topic. So I can add and subtract means. That's logical. I can add variances, assuming my events are independent. I cannot add my standard deviations. And so I have a couple problems that will hopefully get to that. And that's a little bit at times difficult for my students. So this is an oldie but goodie. This is from the 1997 exam, actually the Acorn book. And I actually sometimes give this to my students before we've talked about random variables. I just sometimes like to give them a problem and see what they can do with it. How's that? And so this one is an oldie but goodie. I really like this. And that being said, my students don't like this. They don't like this nomenclature here at the top. X and probability that big X equals little x, Y, probability of big Y equals Y. They don't like the nomenclature at all. And so sometimes this is, what I might call like, a good classroom problem where we do it together. But when I give this to them and give them 5 minutes to do this, they typically do not like this at all. So give me just a second here. Okay, So there's the same problem here. Sorry, there was like a little green outline in my screen. I don't know if you saw that. So here's the same problem. So we have some tables up here: x, probability of x equals little x, probability of y equals little y. I'll demystify that. The tables above show part of the probability distribution for random variables x and y. So the big X and the big Y, those are my two different random variables. That's all they are. If X and Y are independent, super important, and I'm probably going to underline that. And the joint probability that big X equals 3 and big Y equals 4 equals 1/16, then the probability that big random variable Y is equal to 1 is equal to, and honestly, my kids really, my students struggle with this. So big X, that's one of my random variables. Big Y is my other random variable. And over here on the side, I've just tried to demystify. The probability that big random variable X is equal to 1 is 1/6. So that's what that line's trying to tell me. The probability that big random variable X is equal to 2 is 4/6. I think I just made 2/3, 4/6. The probability that big random variable X is equal to 3 is I don't know. Well, you can see that I did a little sigma equals 1, meaning if I add up my three outcomes, my only three outcomes, I have to get 1, right? We talked about that a little earlier. So that was 1/6. So this first question mark over here is 1/6. I think if these numbers were all the same, which they're not, that's a good thing. I think it's real easy for students to say 1/4, 1/4, 1/4, and 1/4. That doesn't have to be true. The probability of each one of these outcomes in a random variable does not have to be the same. And that's why I like X so much over here, is those three probabilities are not all the same. So I set up a little equation here, and I said the probability that big random variable X is 3 times the probability that big random variable Y is 4 is equal to 1/16. I was given that, so I was told that. Well, the probability that big random variable X is 3, that's 1/6. So I felt comfortable with that. Feels like I'm kind of solving for this. So 1/6 times this number here is 1/16. I think I just multiplied both sides by 6, multiplied both sides by 6. And I get 6/16 is the probability that big random variable Y was a 4. So I'll just go and fill that up in here. So 6/16. And again, I do know that if I add these four numbers here, I would get 1. I know that the sum of my discrete outcomes is always going to be 1. So I think I just made that 4/16, 4/16. So this number plus 4/16 plus 4/16 plus 6/16 has to be 16/16 or 1. And so when I was said and done, I did the math. I said, well, the probability that big random variable Y was equal to 1 is 2/16 or 1/8. So my answer was A. I just love this problem. It really helps my kids sort of feel comfortable with this nomenclature, my students, that what this nomenclature is. They don't like it at first. And if I can demystify it, then they feel much better. So here's another multiple choice problem, actually from the same booklet. So this is another oldie but goodie. And my students will get mad at me on this one. So we've talked about at this point of the course adding means. Can we subtract means? Can we add standard deviations? The answer is no. We can add variances, assuming my events are independent. So I usually give them this problem the next day. And unfortunately, many of them get it wrong, and they get really, really mad at me. And then we talk about it, and then they'll sort of maybe reluctantly agree that, yeah, you're right, Mr. Murphy, we should have known better. So for college-bound high school students in 1996, the nationwide mean SAT verbal score was 505, so the average. Standard deviation of about 110. And the SAT math score was 508, with a standard deviation of about 110. The math score over the last 20 years, that average has actually creeped up a little bit, which is actually fantastic. That I think is around 510 or 511. Please don't quote me on that, but it's gone up a little bit. And it may not seem like 3 or 4 points is that much, but when millions of students take an exam, to get any increase at all is actually fantastic. So we've been doing a good job getting that math average SAT score up a little bit. English, I don't know as much about, so I'll leave that up to my colleagues who teach English. But so the average verbal score English was 505, and the average math score was 508. So that's good. Students who do not do well, students who do well on the verbal portion of the SAT tend to do well on the mathematics portion. Super important sentence. Unfortunately, sometimes my students sort of overlook that, but we'll come back to that. If the 2 scores for each student are added, the mean of the combined scores is 1,013. And so that's just adding this 505 and the 508. So I can add means. What is the standard deviation of the combined verbal and math scores? Well, I can't add standard deviations, but I can add variances, and if I square a standard deviation, I get a variance. If I take the square root of a variance, I get a standard deviation. And so almost to a student, they want to circle C, and they'll say, well, Mr. Murphy, we had a standard deviation, so I squared that. Well, now it's a variance. Yep, that's a true statement. We have another standard deviation, Mr. Murphy. We square it. Yep. So we can add the variances, and they like C. Unfortunately, that's not the correct answer. The answer is E. And again, they sometimes get a little vocal with Mr. Murphy and say, Mr. Murphy, we just covered that. You told us yesterday that you cannot add standard deviations, but you can add variances. Yep, that's a true statement. Assuming my events are independent. And I always stress that. I really, really stress that. Well, if we go back to that sentence, students who do well on the verbal portion of the SAT tend to do well on the mathematics portion. I think that sentence right there is basically saying that those 2 events are not independent. And so that's why the answer is E, and super, super important. So before we can add variances with random variables, we need to make sure that my events are independent. And so you know, they sort of reluctantly say, yeah, you're right, Mr. Murphy. We did talk about that. And, you know, almost inevitably one student will say, so every sentence is important. And I like that. I think that's a real important point to make. That sentence was there strategically. It's there for a reason. And read each sentence and say, you know, is there important information here, or is it just setting the stage, or what? So super important sentence, and that's what led me to E. How's that? So another great problem that I really like. So this is from the 2007 exam, and this starts out and says random variable X is normally distributed with a mean of 10 and standard deviation of 3. So I just underline those. Random variable Y, again, many times our random variables are uppercase letters. We saw that, I think, in the first problem. Is normally distributed with a mean of 9 and a standard deviation of 4. Okay, so I have two different random variables. I know the 2 different means, and I know the 2 different standard deviations. If X and Y are independent, okay, that opens up the door, allows me potentially to do some mathematics. Super important. Which of the following describes the distribution of Y minus X? Y minus X. Well, I can add means, and so I can probably subtract means. So I think I said 9 minus 10 is -1. So that felt good, but my students don't struggle with that. So I think I'm just going to cross out a couple of answers here. I don't think it can be A, or I don't think it can be D, because they said 1 and 1. So -1, -1, -1. I can't add standard deviations, but I can add variances. So I think I squared my 3, and I think I squared my 4. Now, many times my students want to subtract here. Mr. Murphy, you subtracted the means, the averages. Why don't you subtract the standard deviations? Let me just finish the problem, and I'll address why we can't do that. So I did add 3 squared, which is now a variance, to the 4 squared. Now it's a variance. And so I guess 25 is my combined variance, but ultimately I want a standard deviation. So if I take the square root of the variance, I get a standard deviation. So I think my mean was -1 with a standard deviation of 5. And so the answer is C as in cat. And that year, 2007, 39% of the students got this problem correct. So this was considered a harder problem. So, there's some nice distractor answers up here, -1 if we just maybe subtract the standard deviations or something, or add them. And so just be careful here. So I guess the question is, when we're subtracting means, why are we adding the variances? So I have a good friend, Dave Bach. He's a College Board consultant, and he's very active in the AP Stats world. This is an example that I think I probably took from Dave, so I'll give Dave credit. So if I have a 20-ounce box of cereal here, I'm pretty convinced when I buy it at the grocery store, there's 20 ounces of cereal, or pretty close. I know that it will vary. I know that it's probably not exactly 20 ounces in every cereal box, but I'm reasonably convinced that it's pretty close to 20. How's that? So if I want a bowl of cereal in the morning, let's say I have a 3-ounce bowl of cereal. I'm going to pour some cereal into my little bowl here, right? Now, when I say I want 3 ounces of cereal, I don't measure it. I don't shake the bowl and level off the top. I flip it over and I dump it in, and when it looks like it's about full, I kind of stop. So I've subtracted from my original 20, and I was reasonably confident that there was pretty close to 20 ounces of cereal in there. After I've taken away, I think there's around 17 ounces of cereal left, but I'm less confident with that. Okay, I'm less confident with that. There's potential more variation there, right? Like, there's probably not exactly 20, but I'm reasonably confident it's close. I definitely didn't pour exactly 3 ounces in, unless it was just dumb luck, right? So even though I'm subtracting here, I actually have maybe greater variation or greater variances. And so that's why, even though we were subtracting the means, we're going to add the variances. So one of my students yells out, "So Mr. Murphy, we're pretty much always going to add variances, whether we're adding or subtracting the means." And I think in this course, that's a true statement. So hopefully that helps a little bit and demystifies that concept. And I will say that that's harder for my students. They will struggle with it. I use all 3 of those problems every year with my students, and I'm hoping that after doing them, they feel a little bit more comfortable. So I got a couple of free response. We'll finish up today doing some free response. This is from the 2001 exam. This is sort of a maybe business type problem. So very real world, very real world. So a department supervisor is considering purchasing one of 2 comparable photocopy machines, A or B. The photocopier at my school breaks down all the time, especially when I need it. I don't know if your teachers complain about it, but it's just one of those things. Maybe it's Murphy's Law. It never seems to work when I need it to work. And it feels like the copy repairman is in almost every day, and I know him by first name. We're like best friends. Machine A costs $10,000, so they're not inexpensive, and machine B costs $10,500. So it's 2 different costs for the 2 different machines. This department replaces photocopy machines every 3 years. In a large school, it would be not atypical to get over 1 million copies in 3 years at a school. So they get a tremendous amount of use. Lots and lots of teachers making lots and lots of copies. They get used quite often. The repair contract for machine A costs $50 per month. and covers an unlimited number of repairs. So if it breaks down once in a month, I pay $50. If it doesn't break down at all, I pay $50. If it breaks down every day, I pay $50. So that's one plan. That's one way that our school could purchase a copy machine. The repair contract for machine B costs $200 per repair. So I guess I'm trying to figure out like which plan is going to be more cost effective for my school over the next 3 years. There's 2 different initial costs for the machines, and I guess there's 2 different potential repair costs for the machines. Based on past performance, the distribution of number of repairs over a 1-year period for machine B is shown below. So it looks like maybe machine B, we can either have 0, 1, 2, or 3 repairs. I wish our machines were that good, were that dependable. It feels like ours break a whole lot more than that. Here's the associated probabilities. And again, I would probably just add those up, 0.75, 0.901. So we talked about that. The sum of the probabilities of a discrete random variable always needs to be 1. And I just want to kind of confirm that. You are asked to give a recommendation based upon overall cost as to which machine A or B, along with its repair contract, should be purchased. So you have to make a recommendation to your principal in your school, should you purchase machine A or should you purchase machine B? And this is super real world. Do we get a variable mortgage or a fixed mortgage when you buy a car? So this is a great problem. Anyone who's heading off into the business world or studying business in college, you'll do thousands of these problems. What would your recommendation be? Give a statistical justification or support your recommendations. Even if that last sentence wasn't there, please always show your math. I'm sure Luke is saying the exact same thing. So for machine A, cost $10,000 to buy. It was $50 a month. It was 12 months in a year, and it was over a 3-year window. So I multiplied 50 times 12 times 3, and I got $1,800. So the total cost for machine A with repairs for 3 years is $11,800. Keep in mind that that's unlimited repairs with this option. Okay, machine B, its initial cost was $10,500, so a little bit more. But the repairs, we don't really know perhaps how many repairs there would be. So I had to calculate the expected value. So down here I said, the outcome times its probability, plus the outcome times its probability, plus the outcome times its probability. And so we expect, so we would call this the expected value, right? Expected number of repairs. We would expect 0.85 repairs a year. Now I mentioned, I think on Monday, we do not want to round that number, okay? And students say, but Mr. Murphy, you can't have 0.85 repairs, and that's a true statement, but we do not round expected values unless specifically told otherwise. So I think there's my initial cost for machine B. There's my expected number of repairs per year, 0.85. We were told it was $200 a repair, and we want to do this for 3 years. So when I did that math, I got 10,500 plus 510, 11,010. And so if I'm looking at these two numbers here, clearly machine B is, well, let me rephrase that. We think that machine B will be less expensive, but there's no guarantees. But most of my students will say, let's pick machine B. And so over here, I just added a sentence and said, I would choose machine B as I would expect to pay around $11,010 over the 3-year window as compared to $11,800 for machine A for initial purchase and repairs. So that's what most students will pick. That's what most of my students will answer. You could make a strong argument that this is a better plan because it has unlimited repairs. So in other words, machine B, if you have not 0.85, that was what we expected, but maybe you could have 10 repairs a year. Well, that would be 10 times 200 times 3. That would be a whole lot more expensive. So this is a problem that you could actually answer 2 different ways, depending upon your perspective. I argued on what I expect to spend. This would be less than what I would spend here. But I think you could have a strong argument saying, you know, even though this plan is around $800 more expensive, it's safer, perhaps. And the fact that it covers unlimited repairs. So it's a really neat problem, because I think you can argue it or present your answer sort of 2 ways. And that's very, very real world. You know, fixed mortgage versus variable rate mortgage. You know, do you lease a new car? Do you buy a new car? Do you rent? I mean, there's all these options, and some of it depends upon your financial comfort level. So kind of a neat problem where I had to use expected values and probabilities and whatnot. And so I really like that one. Let's see if we can do at least 1 or 2 more. So this was from the 2015 exam, sorry. So a little bit more recent. A shopping mall has 3 automated teller machines, ATMs, just setting the stage. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Okay, that makes sense. It is frustrating, right? When you go to an ATM, you put your card in and it tells you that the machine's not working. Let the random variable X, okay, so again, typically uppercase, represents the number of ATMs that are working when the mall opens on a randomly selected day. So I like the randomly selected. Big X is my random variable. And I have three machines, 3 ATMs at this specific mall. So this little table down here, number of ATMs working when the mall opens, none, 0. That is an option, and sometimes students forget that. You know, sometimes students say 1, 2, or 3, Mr. Murphy. Well, I guess none of them could be working, and that would be terrible, right? I'd have to walk around and to go to 3 or 4 different machines, and none of them would be working, right? Probability of that is 0.15. 1 machine working, 0.21, 2 machines, 0.40, 3 machines, 0.24. When I first did that, I thought that actually number might be higher, but it does look like, just looking at these numbers, that many times not all 3 machines are working. How's that? I think I'll add those up real quick, and looks like I get 1. That's sort of good. That happens with random variables, so I felt comfortable about that. And so part A, this maybe was I don't know if I did, I don't think I did this one on Monday, but maybe part A and part B are more what I did Monday, but it's a nice problem, so I want to do all 4 parts. What is the probability that at least 1 ATM is working when the mall opens? Well, 1 working is at least 1, 2 working is at least 1, 3 working is at least 1. So I think in part A, I said the probability that my big random variable X is greater than or equal to 1, at least 1 machine is working. I just added those 3 probabilities and got 0.85. Again, notice that I have those numbers on my paper. I want to make sure that I'm showing the reader my mathematics. And then sometimes I step back and say, you know, is that enough, or should I probably include a sentence? And I wanted to include a sentence. So the probability that at least 1 ATM is working when the mall opens is 0.85. So that felt relatively easy. I was confident that I could do that relatively quickly, but sometimes we just see, you know, 0.85, and students have added those 3 numbers on their calculator. And I'm going to say, to be safe, show us your work, show us your work, show us your work. How's that? Almost never will showing your work hurt you, and almost always showing your work will help you. So just be careful about that. I think I would show that work, and that's what I tell my students. What is the expected value of the number of ATMs that are working when the mall opens? Okay, so outcome times probability plus outcome times probability plus outcome times probability plus outcome times probability. So you see I did that math here. And I think I had the expected number of the number. Well, that didn't make sense. I crossed that out and said, well, the expected value, much better, Mr. Murphy, the expected value of the number of ATMs that are working when the mall opens is 1.73 machines. And again, I do not want to round that. I know that 1.73 machines cannot be working at one time, but that's not what the expected value or mean or average tells us. So I'm going to leave that alone. I am not going to round that at all. And if you did, you would lose some points. We consider that a not fully understanding the concepts. And so please don't round expected values unless specifically told to. What is the probability that all 3 ATMs are working when the mall opens? So all 3 are working. Given that, well, boy, that sounds like that conditional probability that we talked about Monday, doesn't it? That's my red flag right there. Given that at least one ATM is working. Well, at least one ATM is working. I sort of just cover up the 0 and say, well, at least one, at least one, at least one, and I want to know all 3. So the probability that X is equal to 3, i.e. 3 machines are working, given that at least one is working, X greater than or equal to 1. I had my 2.24 was my numerator, that's 3 working. My denominator was adding up those 3 probabilities. I got 0.24 over 0.85, and I just went to my calculator and said, that's equal to 0.282. That's actually lower than what my gut would have said, but it feels like these machines break often. And they said up here that, you know, they sometimes stop working and need to be repaired. So that my gut said it would have been higher, but that's the numbers, that's what it is. And again, I wanted to have our sentence here. The probability that all 3 ATMs are working when the mall opens, given that at least one ATM is working, is 0.282. And in some ways, I'm just repeating the language in the question. But I have my context in here. You know, I've shown the reader some math, et cetera, et cetera. And I think hopefully that's a relatively strong answer that would get a lot of credit, if not full credit. Given that, well, it sort of feels like another conditional probability. Given that at least one ATM is working when the mall opens. Okay, so I guess I have either 1, 2, or 3. Would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? Well, the expected value from part B was 1.73. My gut said it was going to be more. If I say, well, we can't include 0, and these are my only 3 options, it felt like each one of those probabilities might have to proportionally be greater or larger, because those 3 had to add up to 1. So if each one of those numbers gets a little bit bigger proportionally, it feels like when I multiply 1 times a little bit bigger number, plus 2 times that number, which is a little bit bigger, plus 3 times that number, which is a little bit bigger, it feels like my expected value wants to be a little bit greater. So given that at least one ATM is working, again, that means I can cross out that column right there. When the mall opens, the expected value of the number of ATMs that are working would be greater than the expected value from part B, which is 1.73. So I've answered the question, but I think I want to give a little bit more info. By eliminating the probability of 0 ATMs working, the probability for 1, 2, or 3 ATMs working would all increase proportionally, and so therefore I would have a higher expected value. So that was a little different. That wasn't sort of a standard or typical answer. That one I had to think about, and I sort of really like that one. You know, every once in a while, it's really nice to have a challenging problem, even as a stats teacher. So I don't know if I can walk through this one. It's an entirety, but I'll do my best. This is from the 2002 exam. There are 4 runners on the new high school team. The team is planning to participate in a race where each runner runs a mile. So I don't know what you'd call that, the 4x1 mile or something. I guess, you know, runner A runs a mile and then runner B runs a mile. So it's going to take a while. It's going to take a while for all 4 runners to run a mile. The team time is the sum of the individual times for the 4 runners. So I add runner A, runner B, C and D, or 1, 2, 3, 4 to get the team time. That makes sense. And I can add means, right? We talked about that. Assume that the individual times of the 4 runners are independent of each other. Super important. I'm going to underline that. The individual times and minutes of the runners in similar races are approximately normally distributed. That's good, with the following means and standard deviations. So runner A runs a mile in 4.9 minutes. That's actually a pretty good mile. You know, that's really hard to do. These are all under 5-minute miles. These are pretty good runners. And there's their associated standard deviation. So it looks like runner 3 is perhaps the fastest runner. Runner 3 thinks that he can run a mile in less than 4.2 minutes in the next race. A 4-minute mile is 4.2 minute mile is really hard for high school students, really hard for anyone. My gut says it's not likely to happen, but of course I need to do some mathematics, right? Explain. So I said the probability that the time is less than 4.2 minutes is the probability that his z-score is less than, and I just calculated a quick z-score, 4.2 minus 4.5 over a standard deviation of 0.14. What's the probability that the z-score is less than 2.14? Or more than 2.14 standard deviations below the mean. So I just went to my calculator real quick. Normal CDF, -10, -2.14. Now, your teachers may have taught you to type in a different number here. You know, -1,000, minus 2.14. You can see that this number really isn't going to change much, if at all, no matter what my, I guess, lower bound is. And I know sometimes, you know, teachers do 1 times 10 to the -99. I'll leave that up to you and your teachers. What I actually want my kids to think about is, well, why isn't that probability going to change, right? You've changed the lower bound, Mr. Murphy. Well, 10 standard deviations below the mean is pretty much not likely to happen, almost impossible. And so 1,000 standard deviations below the mean is even less likely. There's not much area under the normal curve. How's that? So sometimes I will say to my class, everyone pick a different lower bound, you know, -10, -20, -30, -5,811, really doesn't matter. So I said it is unlikely that runner 3 would run a mile in less than 4.2 minutes. This would only happen about 1.6% of the time, so this is very unlikely. So could it happen? Yes. Is it likely to happen? And the answer is no. So runner number 3 probably is not going to run in the next race a sub 4.2 minute mile. The distribution of possible team scores is approximately normal. That's good. What are the mean and standard deviation of this distribution? Well, I can add and subtract means, and so I just found the 4 means for the 4 runners and I added those. And so I felt pretty confident that 18.9 minutes would be the mean or average time. Again, each runner runs a mile, the next one runs a mile, next one runs a mile, next one runs a mile, and I add up those 4 different times. So I can add means. I can't add standard deviations, but I can potentially add up the variances, assuming that my events are independent. Well, their times in this case are independent. So I did underline that, I circled that. So I felt good about that. I felt like, okay, we were told that each one of those runners' times is independent. So I took the first standard deviation and squared it. I took the next standard deviation and squared it. Took the next standard deviation and squared it. So that's a variance, that's a variance, that's a variance, that's a variance. I added up, I guess, my combined variance. I take its square root and I get the standard deviation. So that's part B. What is the mean and standard deviation of this distribution? The mean would be 18.9 minutes. Standard deviation would be 0.3003 or 0.30 or something like that. Let me see if I can finish the last one real quick. Suppose the team's best time to date is 18.4 minutes. So their mean or expected time is 18.9 minutes. Can they run an combined 4 miles, 18.4? My gut says no, but again, I need to do some mathematics. What is the probability the team will beat its own best time in the next race? I said the probability that the team time is less than 18.4 minutes is equal to the probability of your z-score being less than 18.4. That's the time they want to beat. That's their mean or expected value time, 18.9. There's my standard deviation. probability that Z is less than 1.655, so smaller than 1.665 standard deviations below the mean. Again, I went to my calculator and I typed in -10, but you could type in -100, -1,000, whatever your teachers pretty much taught you to do. That's perfectly fine. Your answer is probably not going to vary. And that was 0.04795. And you know, as a stats teacher, we just did inference a couple of weeks ago, and I wanted to compare that to 0.05, but this problem didn't really ask me to do that. So I wanted to, and there was no need to do it here. So the probability that a team will beat its own best time, 18.4 minutes, in the next race is 0.04795. I have context, I have a full sentence, I have some mathematics, and I sort of went down the wrong path here with the 0.05, and I was thinking alpha is 0.05, that's the inference teacher in me. And I don't need to worry about that for this problem. But if it were an inference problem, boy, that's really close to that typical standard alpha of 0.05. And, I'd have to make a decision. And if it was lower than that, I would reject the null hypothesis. But it has nothing to do with this problem, so let's not go there. So anyway, those were, I think, all of the problems that I had for random variables. So let's just check to see if we've done them all. I think we have. So that was good. So real quick, hopefully you're feeling more comfortable with solving different types of random variable questions. I'll just open that up and say probability. Between the probability I did Monday, Luke did binomial and geometric yesterday, and I did some random variables. Hopefully probability you're feeling much more comfortable with. Similar to all problems in AP Stats, you should be able to write down a clear, concise solution in context. It's so important. And every year when we grade problems, we see, unfortunately, students will lose a point, sometimes 2 points, for lack of context. They don't have context. They have some numbers, they have some math, but there's no context, and super, super important. So here's tonight's homework. It's from the 2012 exam, and we're doing some sort of a transformation here, and we want to know what happens to the standard deviation. So Luke will do a great job with that tomorrow. So let's just wind down for today. Hopefully you had a good day. Hopefully I helped with some probability and random variables. College Board knows that not all students are going to have access to the internet or a device for the exam, and we really, really want you all to take the modified AP Stats this exam. I think it's on, Friday, May 22nd? The College Board's working on solutions to help students get what they need to show their best work. So please, 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 if you have internet problems at home, you don't have a device, you need a calculator, reach out to your school, your teachers, your administrators, the College Board at the link below, and the College Board will bend over backwards to make sure that we get you what you need. So if you're having mobile tools or connectivity issues, or one of your friends does and they're not quite so comfortable asking for help, please, please, please reach out to the College Board, and we'll try and make it happen. How's that? So thanks for watching. Luke's going to finish up the week. It's our school break up here in Maine, and so I wanted to, see if I could go out and enjoy some of the nicer weather. My wife and I have been taking some day trips around Maine. So we hope that we'll see you again. Luke is doing sampling distributions and central limit theorem tomorrow, and then free response Friday, FRQ Friday. And then next week, we're going to focus on strategies for doing well on the AP exam. We're going to actually grade some FRQs. So on Monday, I'll be back, and I'm going to make you like AP readers. We're actually going to read some student samples and grade them and see what mistakes they made, if they made any at all. So please be safe. Please stay positive. Please take care of your family and yourself. We'll get through this. We really appreciate your watching, and Luke and I sincerely hope we're helping you. So well, let's call it a day. Thanks for watching. You'll see Luke tomorrow and Friday, and I'll be back on Monday. So have a great day. Be safe. Thanks for watching.